Welcome to this lecture on considering radiation effects in near threshold volt circuits. This is a part of module 3. First we will discuss radiation effects and why they are important in near threshold voltage regime, and then we will discuss a model for the critical charge and flipping because of single event upset. So, these near threshold circuits have very small headroom. VDD minus VTH is very small, it can be negative, it can be positive, but it is very small. So, if there is a change in voltage or change in voltage at any node which is not the expected change, the impact of that is much more in near threshold circuits when compared with conventional circuit. The load capacitances store smaller charge values. So, because VDD is small, CVDD is also now small in near threshold circuits. So, smaller charges are present. So, if the value of the charge changes because of say charged particles from ambient radiation, you would find that the change in charge on the capacitances is now or on different nodes is now much larger because the charge itself was smaller. And small changes in voltage would cause exponential changes in currents. So, therefore, because of these reasons, radiation effects in near threshold voltage circuits are much more significant when compared with those in conventional nominal voltage circuits. So, one of the important things to consider is soft errors. So, what are these? For example, here we have an example where an high energy alpha particle strikes. This could happen because of the packaging material itself. For IC packaging material itself releases alpha particles as seen in a lot of literature. So, now this alpha particle strikes. So, this is a PN junction. For example, drain to body junction is a PN junction. So, in the drain to body junction this alpha particle strikes. Now, this is a high energy alpha particle and when it strikes it stops within the lattice. So, its energy is given to the lattice and that energy separates electron hole pairs, because now electrons would be released from the valence band and go to the conduction band because of this energy that has come because of the alpha particle. Now, since electron hole pairs are released in large number, the effective doping density in this region becomes smaller. Suppose the doping concentration is N1 and N electron hole pairs with a concentration N have been released. Now, the effective doping concentration would be N1 plus N, and that is compared with N holes which are already released. So, the effective doping concentration is now smaller. So, that would extend the depletion region. All this is a transient phenomenon. So, that would extend the depletion region. So, once the depletion region is extended, there are electric fields in it, and the electric fields are from this, suppose this is N type, so this is P type. So, the electric field is in this direction from the N type to the P type. So, electrons are pulled into the N type region which could be drain, and holes are pulled out of this P type region and they go into the substrate. So, electron hole pairs are separated now. So, they cannot recombine. So, this causes a large electron current through this N region contact. So, that could be drain node of the device. So, drain node of the device could see a large electron charge, large negative charge coming, and therefore, its voltage is pulled down. So, this is an effect which is seen because of this say alpha particle strikes. That is the example we are seeing here, and this current is seen to have this kind of a nature where it suddenly rises, and then once all the electron hole pairs have got separated, this depletion region again becomes smaller and you come back to the original depletion width, and then there is no electron hole pair generation because the energy has been given to the lattice and all this phenomenon has happened. So, you find this kind of a current because of this alpha particle strike, and this current is modeled with this expression. For alpha particle strike, you would find that tau r is much larger than tau f. So, you will find that this dominates usually. So, this is modeled with this expression where tau f is much larger than tau. So, this is a small initial transient which can be seen, and this is this would evolve in long term. So, initially this is like 1 value 1 because tau f is very large. So, initially this is like 1 minus e to the power minus t by tr. So, it rises and after that this starts dominating and this dies down. So, you find a fall because of this. So, from this point it is this which dominates and initially it is this 1 minus e to the power minus t by tau r which dominates. So, what is the impact of single event upset on a flip flop? So, let us see a latch which is the master stage of the static flip flop. So, this is a vulnerable node. Here suppose an alpha particle strike happens on the drain of n MOSFET. So, then you would see that a large negative charge would appear here and a double exponential, it would look like a double exponential current source as we had seen earlier and the voltage here would be pulled down. So, if the voltage here is pulled down, suppose this was VDD, suppose N1 was initially VDD, so of course this was VDD, then V of N2 before t is equal to 0 is 0 and the alpha particle strike of n MOSFET in transmission gate T1 at t is equal to 0, that is the node N1. Okay. So, that is a vulnerable node. So, once that happens N1 is pulled down. If N1 is pulled down, then it could happen that N2 is pulled up and since N2 goes to high voltage, it could happen that this is the inverter followed by transmission gate T2, it also because its input is high, it also pulls down N1 and finally you have a flip of state that can happen. So, because of the single event upset. So, this is now called a single event upset because an alpha particle has striked here and that has caused a circuit state was upset. Suppose the charge that is generated on N1 because of single event upset is very small. For example, in this node N1 when the value of in, when clock is transparent, suppose the value of in is latched and after that the clock is now in a hold state. So, this is suppose a hold state. So, within the hold state we find that there is this alpha particle strike here. So, there is a single event upset at node N1, but the reduction in the voltage of N1 is small. Suppose it is smaller than the inversion threshold of this MP1 N1 MN1. So, in that case there is almost no change in the voltage of N2. So, let us look at another scenario. Suppose this is the hold state of the latch, that is when clock is 0 hold state. So, suppose the reduction in voltage because of alpha particle strike is quite large. This can happen if the alpha particle, the energy of strike is large or dose is large, energy of strike is suppose large, then you would have more LEHP electron hole pair generation and therefore, you can have the switching happening at node N1 or N1 N2. So, here because of the alpha particle strike there is a large change in voltage and that would cause a flipping. So, because this negative the N1 has been pulled down to such a low value that it P1 now turns on, MN1 is off and the current through MP1 is such large that the voltage of N2 rises and it rises in to such a value that MP2 MN2 also switches, and therefore, there is a complete switch of N1 and N2 from N1 from 1 to 0 and N2 from 0 to 1 logic state. Now, this is a flip which is happening because of the alpha particle strike, which is a random kind of phenomenon. It is not a phenomenon for which is expected in the normal behavior of the circuit. How can we understand this? So, this is the voltage transfer characteristic of MP1 MN1, and this is the voltage transfer characteristic of MP2 MN2 plus T2. So, this is V2 as you can see, and this is V1. So, you find that these two are stable points and this is the metastable point, okay, where the gain of MP1 and both the inverting stages MP2 MN2 and T2 is also an inverting stage, and T2 is conducting in hold state, transparent in hold state. T1 is off in hold state. So, now through this T2, so you have, when T2 is transparent, you have this as the voltage transfer characteristic. So, now this is a metastable point, because here though the V1 and V2 can have this value, but they would both the stages MP1 MN1 and MP2 MN2 in a high gain state. So, a small change in the voltage can actually take the back to back connector inverting stages pair one of the stable points. So, if N1 and N2 can reach close to this metastable point, their final state cannot be predicted. If somehow they come to the metastable point, they would not remain at metastable point for long, because they can be taken by a small noise to either of the stable states, and one cannot predict to which of the stable states it goes. So, in case the single event upset is such that the negative charge on N1 pulls the value of N1 from VDD to this metastable point, and N2 also reaches the metastable point, in that case you cannot predict to which value it will come back. Suppose N1 and N2 are, as we had shown in the previous example, are not pulled down to below the, for example, N1 is not pulled down till this value, and N2 is not, N2 has a value which is smaller than the metastable value, and M1 has a value which is larger than the metastable value, then they will be pulled back to the original state, that we can see. For example, N1 is suppose at this value and N2 is here. So, due to the alpha particle strike, the negative charge on N1 is such that it is here. So, in this case, for it, this would have propensity to pull N2. So, you have pulled N1 from this value to this value, is not this much, and N1 has been pulled down by this much. So, the maximum that N2 can be forced is this value, is not N2. So, N2 has not changed its value because of this, okay. And what would then happen? Then since N2 is at this value again, so that would pull back, that has the propensity to pull back N1 to this value again near 0. So, you will finally come back to again to this stable point. So, unless the charge that is coming on the node N1 because of the single event upset is such large that N1 is pulled to near this value, near the metastable value, you will always be pulled back to the original state. But if it comes here, then with small noise you can be pulled to either this state, either the switched state or to this state. So, it can be pulled down to both, either this or this if it comes to the metastable point. So, therefore, from metastable point it is not predictable to which of the states it can go. So, it is the critical charge is that value of charge on node N1 because of radiation which can cause an unpredictable flip, that is which can pull the values of N1 and N2 to near the metastable value point values, from where you cannot predict to which of the states, which of the stable states the flip flop or the latch would switch to. So, this if we look at in transient simulations, how does it look like? Here the alpha particle strike has happened and therefore N2 is switching. So, now N1 has switched to an ebb value V1 which we are calling, and so now the forward path inverter is its input voltage is now quite low, it is in fact slightly below 0, and it would now pull the feedback path inverter's input voltage high. Okay. And now this is the critical charge. So, for critical charge what happens is this moves to the value which is near metastable point. So, therefore, it is at the metastable point and you find that both are at metastable points, and therefore, in the whole state it can flip to any value, any of the stable values. So, if we look at the transient phenomenon, this is how the metastable point is reached. So, this node N1 should be pulled to a sufficiently low value so that you get to the metastable point. Suppose it is pulled down not to this V1 ebb, but to a lower value of but to a value which is higher, then N2 would not be pulled up to this extent, and therefore, there would be a glitch, but N2 would come back to 0 and N1 would go back to VDD. There would be a glitch of this kind and N1 would go back to VDD. So, it may not in fact like this. Okay. If the charge on node N1 is not sufficient, it is smaller than the critical volt charge. So, this is for Q N1 smaller than Q critical, and this is for Q critical. Now, suppose you increase the load capacitance of the latch. So, for N2 to rise to the metastable value, you would now require a larger charge because you increased load capacitance on N2. So, if you increase load capacitance on N2, you would require a larger current, and therefore, the rise would be slower if you increase the load capacitance. So, this is for increasing load capacitance. Increasing load capacitance of the latch at the node N2. Okay. So, what would happen now? You require a larger charge at node N2 to be supplied. So, therefore, to reach the metastable point, you would require a larger charge, or in other words, the value of V1 which would cause this flipping would be slightly lower. So, as you increase the load capacitance, increasing CL at N2, you would find that the V1 would rise more slowly, and that would cause a larger PMOS current or larger charging current for node N2, and that larger charging current would, because now the load capacitance is larger, to larger charging current is required, because a larger charge is required for V2 to rise to the same value. Okay. So, for V2 to rise to the same value, so V2 would be rising from 0 to this value, and for that V1 would have to begin from a smaller value, so that with increasing load, so that this V2 can rise to the same value. One important thing that we observe in this work is that whatever be the value of the fan out load here, fan out load of N2, which I am also calling CL in the previous slide. So, whatever be the value of fan out load here, your transient at the rate of charging of V2 or rate of charging of N2 would coincide with each other. That is, the rate of supply of charge is just proportional to the load capacitance. The rate of supply of charge is just proportional to the load capacitance. Otherwise, the rate of charging, the transient remains similar for all the fan out loads at N2. So, we use this fact that the transient behavior of V2 does not change with the fan out load, and also it scales with the supply voltage. So, that we use in obtaining an expression for the critical charge. So, now we can write that Cn2 is the total capacitance of node N2, Cn2 dV2 by dt is the current supplied to this. Now, this is essentially supplied by the transistor MP1. Because of SCU, the voltage of N1 has gone to near 0 or slightly below 0. So, Mn1 is effectively off. So, this we can write the subthreshold expression. In this implicitly we can take lambda VDS of this. So, we are dealing with the ebb voltage, that is the lowest voltage of N1, which is required to flip the latch. So, would entail the VDS, magnitude of VDS of this to be VDD. So, suppose this is V1 ebb, which is close to 0 volts, okay, and this is also V2 of this is also 0. So, therefore, you find that MP1 is in saturation. Subthreshold saturation. Okay. So, therefore, you can neglect this term. Magnitude VDS is quite large for this, and in this you have included the DIBL. It is as if DIBL is for supply voltage for VDS being near VDD. So, with this we get that the value of what is the value of VGS here? VGS is V1 ebb minus VDD. So, if you substitute this, you get this value of V1 ebb. This is VDS is nearly equal to minus VDD for the P MOSFET. All this is for P1. Okay. So, solving this we get this expression. Now, in this we know that this is unique, irrespective of fan out load, this does not change, and also this is proportional to the value of supply voltage. For a given fan out load, this is again proportional to the supply voltage. So, if we do a transient simulation with enough tolerance and the time steps should be very small for a given fan out load for the latch and for a certain supply voltage, we can find out this transients, and we know the value of dV2 by dt at time t is equal to 0, that is when the alpha particle strike happens. So, that once you know and you have extracted it, for different values of fan out load it is the same, for different values of VDD it is proportional to VDD. So, you can obtain it again. So, you can estimate the value of V1 ebb by substituting the fan out load here and Cn2 because of the new fan out load, or dV2 by dt because of the change in VDD. So, you can estimate it again and again, and we can also obtain C in, we can write this Cn2 as the gate capacitance here and here, and rest of the capacitance, if we call parasitic capacitance, we can obtain its value from the same expression in this way. So, once we know the value of V1 ebb for a few values of fan out load, we know the value of V1 and we know the values of Cg1 and Cg2. if we extract these two out, then one can obtain the value of parasitic capacitance Cp and write down Cn2 as Cg plus Cp, where Cg is this value Cg1 plus Cg2. So, if one changes Cg1, one can estimate what is the new value of Cn2. So, from the new value of Cn2, then again obtain. So, what is the new value of V1 ebb? That is, V1 ebb is lowest value of V1, which causes the latch to flip. And what is the value of critical charge? So, Q critical charge is VDD minus V1 ebb into Cn2. So, Cn2 is the capacitance seen here. So, one can obtain the gate capacitance and the effective off state capacitance of T1 and on state capacitance, parasitic capacitance here, add them all, one can get the value of capacitance Cn1. VDD minus V1 ebb into Cn1 is the critical charge. So, now this critical charge is, so if we know the value of the critical charge, then one can translate this to the radiation dose, and so therefore, one can estimate what is the critical charge for a given dose and energy of radiation, of alpha particle radiation, and that can be a design guideline. So, this is the critical charge and I want to design for a certain critical charge. So, I will in that case, so I know that which of the flip flops need to be replaced. So, that replaced by more radiation tolerant flip flops or more near threshold voltage resilient flip flops like razor flip flop that we had discussed. So, which of the flip flops need to be replaced by suppose a razor flip flop? If I want to make a design decision, I would estimate the critical charge and see if the critical charge would be normally exceeded. So, from the dose and energy of the particle strike, I would estimate whether the capacitance value here is such that the charge would result in V1 ebb. If it results in V1 ebb, then there will be a flip. So, in this lecture, we discussed the importance of radiation effects, particularly single event effect in near threshold voltage circuits, and we discussed the flipping mechanism of a near threshold of a latch in near threshold voltage domain, and we discussed an approach to estimate the value of critical charge for a given static latch, which is master stage of a static flip flop, which can cause flip of the data in hold state. Thank you.